So, in light of our analysis of the standard second order system, the integral control is helpful, but it may not solve all of our problems. Again, the transfer function that we end up with in that case is exactly of the form of the standard second order system. So, in the underdamped case, we know exactly what its impulse and step responses are going to look like, and what we saw in the last video. Again, the parameter that we can control, that we can choose, is Ki. That is the only parameter of the controller. The rest are physical parameters of the plant, which we can't change. So under our integral control scheme, we can determine the natural frequency, the so-called natural frequency of the response. But we can't determine the damping ratio. We're stuck with this one. Maybe I should explain a bit more why we call the parameter omega n the natural frequency. In the case where the damping ratio is 0, we end up with omega n squared over s squared plus omega n squared. So that is just the transform of a sinusoid whose angular frequency is omega n. So this natural frequency is the frequency of oscillations in the absence of damping. So in this case, we do have some damping because we have a non-zero drag or friction coefficient B, but B and M, the mass of the vehicle, are givens. They're properties of the vehicle we're trying to control. We can't change them. I may have said we can't change the damping ratio. We can change the damping ratio because this B over M that we're stuck with is of course 2 zeta omega n. We can change the value of omega n. We can choose the omega n that we like. And in order to speed the response up, which is typically what we would want to do, we would want to make omega n sufficiently large. But since the value of the product zeta omega n is fixed as b over 2m, the larger we make omega n, the smaller we make zeta. So the faster we make the response using this integral controller, the less damping we're going to have. And that's normally going to be a problem. If we speed the system up sufficiently, we may find that there's far too little damping. We get a big overshoot beyond, in the step response, for instance. If we assume that the reference input is of the form of a unit step, then the step response may overshoot that by a long way, and then it may continue to oscillate for a long time before settling down near its steady state value. So we really need a controller that has more parameters than this and gives us some control over the damping ratio. For that, what we can do is combine both proportional and integral control. This is often abbreviated to PI control. So in this case, our transfer function from the reference input to the speed of the vehicle, which is in general C of S P of S over 1 plus C of S P of S. In this case, we're going to have a transfer function that looks like Kp plus Ki over S. So in other words, our control input U will have a term that is proportional to the error signal and another term that is proportional to the integral of the error signal, combining the two features of the previous controllers. So what does the transfer function from the reference input to the speed look like in this case? There's our C of S. We multiply that by the plant transfer function, 1 over ms plus b, divide through by 1 plus that C of S times 1 over ms plus b. Now, In this case, we're probably going to want to multiply numerator and denominator by s times ms plus b. Got an s in the numerator. We haven't seen that in any of the transfer functions we've studied so far. Downstairs, we will get ms squared plus bs plus kps plus ki, because we're multiplying not only by ms plus b, but by s. So if we group terms together a bit, we'll want to divide by m as well. So we'll get HRV of s equals, let's say, 1 over m times kp s plus ki divided by s squared plus b plus kp over m times s plus ki over m. So this looks like the denominator of the standard second order system. As in the case of integral control, our natural frequency will be the square root of ki over m. But in this case, instead of being just b over m, our term 2 zeta omega n is b plus kp over m. So we have control over the damping ratio in this case, as well as the natural frequency. Let's make this look a little bit more like our standard second order system by having a term ki over m, a factor ki over m in the numerator here. So that means we'll have kp over ki s plus 1 as another factor. And then we have a denominator of the form of our standard second order system. So this looks like the transfer function of our standard second order system, except we've got an extra factor in the numerator. We have this kp over ki times s plus 1. That means that we have a finite zero in our transfer function, as well as the poles. We've already analyzed the effects of the poles. We don't know exactly what the effect of this zero will be. We know we can choose the coefficients in the denominator. So we would normally be able to get the response that we wanted if this were a standard second order system. But the form of the response is obviously going to change because of the presence of this zero. What's going to happen? That's what we're going to analyze principally in this lecture. So we can look at more complex transfer functions by analyzing them in terms of the standard examples that we've already looked at, the standard first order system and the standard second order system. So let's start to see how we can do that. And we'll start with this case that we've just seen, the case where you have a finite zero in your transfer function. Okay, so let's call this transfer function hz of s, z for 0, of course. This is the sort of thing that we just saw for our cruise control with PI control. We can write it of the form omega n squared divided by s times alpha zeta omega n plus 1 over s squared plus 2 zeta omega n s plus omega n squared. And this is a case where alpha is greater than 0. We'll assume alpha is greater than 0. So this alpha is the ratio between the location of the finite zero, namely at minus alpha zeta omega n, so that's a real valued finite zero, minus alpha zeta omega n. And on the other hand, the real part of the poles at minus zeta omega n. So in other words, our zero is alpha times as far from the imaginary axis as are the poles. So our poles are at minus zeta omega n plus or minus j times omega n times the square root of 1 minus zeta squared. And our zero, which we'll denote this way, is at minus alpha times zeta omega n. That means in order to analyze the effect of the zero, we just have to look at this parameter alpha and see how the form of the response changes depending on the value of alpha. Again, the general idea is that any transfer functions more complex than the standard two that we've looked at, the standard first order one and the standard second order one, we can analyze in terms of those standard transfer functions. That's why we wrote this one in this way. It looks just like the standard second order transfer function, but with this additional factor. So how do we analyze this additional factor? For simplicity, let's just look at the step response. We know the impulse response is just the derivative of the step response. And it turns out to be particularly easy to look at the step response. So as always, we get the step response by multiplying the transfer function by 1 over s. Our transfer function in this case is hz of s. So we can write that out this way. We can break up hz of s into a standard second order transfer function. Times 1 over s plus s over alpha zeta omega n times another copy of the standard second order transfer function. Again times 1 over s. Okay. Okay. Now, in this second term, we see that we can cancel out these s's. So what is this inverse transform going to be? Well, obviously the inverse transform, we can transform the two parts separately by linearity. So the first one will just give us the step response of the standard second order system. The second one will simply give us the impulse response of the standard second order system times this term 1 over alpha zeta omega n. So that's what we end up with. Of course, the zero gave rise to this additional term S over alpha zeta omega n. We know that multiplication by S in the Laplace domain, in the case where all initial conditions are zero, corresponds to differentiation. So that's why it turns the step response into an impulse response. And then we're dividing by this alpha zeta omega n. So that's going to control the amplitude, if you like, of the scale factor that's applied to this copy of the impulse response of the standard second order system. So again, the general idea is that when we have a more complex transfer function to analyze, we can analyze it in terms of the standard examples that we've already seen, and we see that here. We just end up with a step response of the standard second order system plus 1 over alpha zeta omega n times the impulse response, again, of the standard second order system. Okay, so there's a plot of the kind of the kind of response that you get in the notes. I'll just here point out that as, say, alpha goes to infinity, the size of this copy of the impulse response, the term by which it's weighted here, goes to 0. So as alpha goes to infinity, in other words, as the 0 at minus alpha zeta omega n goes to minus infinity, the 0 moves off to the left, the response approaches that of the standard second order system. So we fail to see the effect of the 0. So as alpha gets large, the 0 doesn't have much effect. We can neglect it, in fact. You might typically do that if the 0 were, say, 10 times further from the imaginary axis than the poles. Its effect on the response could be ignored. I should be a bit careful about that. On the transient response, I would say. You still have to take account of it when you're doing things like finding, say, the final value of the response, that sort of thing. Well, in this case, the final value is again going to be 1, but there are times when you'll still have to take account of the 0. Its effect on the transient response can be ignored, and it won't have any effect on the steady state response. But what if alpha gets very small? Well, then, of course, this term 1 over alpha zeta omega n, by which the copy of the impulse response of the standard second order system is multiplied, goes to infinity. So we see, for example, much more overshoot of the step response beyond its steady state value. It doesn't affect, of course, things like the damping of the oscillations or the frequency of the oscillations, but if alpha is small, it can give us much more overshoot. So that's something we would have to take into account, for example, in our cruise control system example. So we're going to get a lot of extra overshoot if alpha is small. So what we might do is choose the two parameters. First, we choose Ki for speed of response because Ki determines completely the natural frequency. Then given that value of omega n determined by Ki, we would choose Kp for a damping ratio. And knowing that the zero may add overshoot, what we would do is probably go for a higher damping ratio than otherwise. What is our value of alpha, zeta, omega n in this case? Well, the term in our numerator is Kp over Ki s plus 1. So alpha, zeta, omega n is Ki divided by Kp. Okay, so if, for instance, we choose a Kp that is quite large relative to Ki, well, we'd have to take into account the real part of the poles too. But if this quantity is small relative to zeta omega n, or if it's, as long as it's not large relative to zeta omega n, we'll see this effect of increased overshoot. So for that reason, we'll want to choose our Kp to give us a larger value of zeta than we might choose if it weren't for the zero. So we'll just have to try to compensate in advance, if you like, for the fact that depending on the value of alpha, zeta, omega, and the zero may give us a larger overshoot. Of course, we can do our design in an iterative way. We'll choose Ki and Kp, see what kind of overshoot we get. If there's too much, we will increase Kp so as to increase the value of zeta, and then simulate the response again and see what we get. So that's a quick look at one aspect of analyzing more complex transfer functions in terms of the standard transfer functions. We added a zero to the standard second order system transfer function, and we saw that the step response that we got equaled the sum of the step response of the standard system plus 1 over alpha zeta omega n times the impulse response of the standard second order system, where the zero is at minus alpha zeta omega n. In the next lecture, we'll see what happens when instead of adding a zero to the second order transfer function, we add an additional pole. See you then.